So welcome to lecture number 12 of statistical thermodynamics. So as we saw that the hydrogen spectra could be explained by the Bohr's model. So let us see how that can be explained by the Bohr's model. So let us take a very simple system. Okay. So this is the orbit of an electron. And this is, say, the central nucleus, which has got a positive charge, plus minus. Okay. And so the radius is given as r. Okay. The electron is moving in this particular direction with a velocity v. Okay. Let's call that v. And of course, there is an inward force because the electron is moving. Right. Let's call that inward force as Fe. So what we do, this is a very simple system in which there is a nucleus. I mean, let's take the hydrogen, for example. So this is the nucleus which is positively charged. The electron is moving around the nucleus. It's like a single electron kind of a system because hydrogen. And it moves with a velocity v. Okay. And so what we do is that we apply Newton's second law here to this particular system. Right. So let's write the force Fe. Fe is nothing but an electrostatic force. Okay. Because it's a positive negative charge. Okay. And then that electrostatic force is given as E squared by 4 pi E naught R squared. Okay. As the electrostatic force, E is nothing but the charge. Okay. And this should be equal to the centripetal force, okay, which is given as me into V squared divided by R. So this is basically this particular part of the term is called centripetal acceleration. Okay, so this is the electron mass. Okay, so you have what we have over here. You apply Newton's second law to this particular system, which has got an electron which is rotating around a nucleus, which is composed of a proton. The velocity of the electron is v. So there is an electrostatic attraction, okay, which is given by Fe, and then of course there is a centripetal acceleration, which basically balances this electrostatic force of attraction. Right? So Te, if I project Te as the kinetic energy of the electron, okay, that is equal to half me v squared. Okay, me is basically the mass of the electron, okay, which is also equal to now e squared by 8 pi epsilon naught into r, as you can see from this particular expression. Okay, I just add a half to it, and you can see that this is how it comes. Okay, because of this balance, we can write it like this. So therefore, VE, which is basically, say, the potential energy, this is different. It's not the velocity. Potential energy, okay, that is given by, so this is the kinetic energy of the electron, that is the potential energy of the electron. So it is from infinity to r. If you bring an electron in, it is E squared by 4 pi epsilon naught dr by dr squared. All right. Okay. So this is the force field. This is the electrostatic force field. So this is the potential energy, which is equal to therefore minus E squared divided by 8 pi epsilon naught into r. Right. Okay, so this is the potential energy. So the total energy of the electron, okay, is given as the total energy E is is T plus V, so it's kinetic energy plus the potential energy. If you add the two, it will be E squared by 8 pi epsilon naught R. Okay, so this is the total energy of an electron which is orbiting around a nucleus. So what did we do? We first balanced the electrostatic force with the centripetal force, and then we calculated the kinetic energy of the electrons, and we calculated the potential energy of the electrons. This is the energy that is spent to bring the electron from infinity to a radius r. Okay, so this is the standard definition. So this should be the energy of the electron. Okay, now Bohr had the following postulates. So these are postulates, remember. So he said that the angular momentum is quantized, where this is nothing but nh into 2 pi, okay, where n is equal to 1, 2, 3. So n is an integer, as we all know. So n is an integer, so that is the integer representation. So the angular momentum is quantized. So it basically says that the angular momentum is quantized. Okay, so this is the first postulate of Bohr. Okay, and then of course the second one is that transition from lower to higher orbit, okay, is given by, we already saw this. This is the wave number. It's energy En minus energy Em divided by Hc. This is basically delta E. So this is the higher energy, and this is the lower orbits. This higher orbits. Okay. So what did Bohr did apart from this? He said that the angular momentum is quantized, and it is given by this particular form, which is nh by 2 pi. N are integers, so naturally this is quantized. So this can have discrete values only. And transition from higher to lower orbit is given by this, which is nothing but the differential of energy. This is delta E basically. This is higher orbits, and these are the lower orbits. Okay. So armed with this, okay. So what will be the form for V? So let's look at V. Therefore, V is equal to NH bar divided by ME into R. Okay, because of the quantization, from the quantization we can say V is equal to NH bar by MER. That is exactly what we have written. So therefore, TE is equal to half MEV square. Okay, which is further represented as half ME. Okay, let's put it as NH bar by MER square. Okay, so now if you substitute from the previous expressions, it will be E square by 8 pi epsilon naught R, where R, therefore, this is also equal to R. So R, therefore, if you equate the two, will be given by 4 pi epsilon naught H bar square divided by M E square into N square. Okay, so basically we have equated the two, okay, and we have substituted for V, which is given by this particular form. So this additional form, if you can look at it here, from here it was not quite evident that how the quantization comes into the picture. Here you can be clear that because the angular momentum was quantized, this readily offers an expression to calculate V, and V can be now further substituted in the kinetic energy term, and therefore, now equating with the existing expression for kinetic energy, which we already did over here, taking this and equating these two, okay, we get a definition for R, okay, where n is equal to 1, 2, 3. So as you can see, R is naturally quantized, right? Therefore, En, the energy at any particular nth energy level, is therefore 2 pi naught me e square divided by 4 pi e naught h bar square n square. All right, that comes from the expression that we just now saw here, right? Or in other words, En is given as minus me e to the power of 4 divided by 8 epsilon naught square h square n square. Okay, all right. So this is the energy at any particular energy level, okay, and it is given by this particular expression that we have over here. Okay, now if the energy is written in this form, in a wave number space form, it is given as minus me e to the power of 4 divided by 8 epsilon square c h cube into 1 over n square. This 1 over n square is very important because this is where the quantization comes. Therefore, gamma nm is given as me e to the power of 4 divided by 8 epsilon naught square c h cube. Then let us change the font, 1 over n square minus 1 over n square. Okay, so this particular guy that you see over here is supposed to be the Rydberg constant. Okay, so what did, and it indeed turns out to be a very accurate estimate of the Rydberg constant, right? Okay, so as you can see, therefore, in this particular expression, that this RH is now represented by this. So just let's do a very quick recap. So what happened was that we first cast this very simple system of an electron rotating around a nucleus. We applied Newton's second law, in which the electrostatic force was balanced by the centripetal acceleration. And then we cast the kinetic energy of the electrons is given by this. And the potential energy is given by this form. This happens because in a conservative system, this is the energy that is, so if you bring the electron from infinity to all the way up to R, and that is what gives you the potential energy. Okay, that is what gives you the potential energy for a conservative system from infinity to R. So now that gives you now the total energy. The total energy is nothing but the sum total of the kinetic energy and the potential energy, which is given as this. Okay. So then we move on. Now that we have got this all sorted out, then we went to the Bohr's postulates. So in Bohr's postulate, what did Bohr say? That the angular momentum is also quantized, and it is given in this particular form, where n is basically the integer through which the quantization happens. And transition from lower to higher orbit is given by this. This is nothing but the delta E. Okay. And therefore, using this particular expression now, which is the quantization of angular momentum, we found an expression for V, which is the velocity, right? So the kinetic energy is therefore given as this, and kinetic energy already found is given in this particular form. So equating these two, okay, we found that what will be the allowed radii, the allowed radius of the orbits. So we can write it as a radii of allowed orbits, correct? And this happens through the quantization of n equal to 1, 2, 3. So you cannot have all orbits. This is given in discrete forms. that energy now, any energy can be now, if you look at this particular expression, the total energy, right? The total energy, you substitute the expression for R in that expression. That's basically you put this here and you get this expression for energy. Okay. Now, you can, this is just algebraic manipulations. And then once you, so the differential, so when you normalize the energy, this is, it comes into the wave number space, and then you find out what is a wave number for a transition, for an allowed transition. So therefore, this constant that sits in front should be the Rydberg constant, and this is exactly what it is, because this matches with experimental data. Okay, so you can understand what we did over here. Okay, just if you don't, so the energy, let us write this expression quickly so that you get an idea that when we say energy, what do we exactly mean. So energy, if you recall, was given as minus E squared 4 pi epsilon naught, or rather 8 value, sorry. 8 pi epsilon naught into R, and R we found out was given as 4 pi epsilon naught H bar M E square N square. Okay. Now, if you substitute this here, that is how we get the energy of any nth energy level as ME e to the power of 4 8 epsilon naught square H square N square. This is how you get the final expression. Okay, so you just put this right here, rather expression for this right here. So that's how you get the energy. So what we have got over here, we have got an idea of the allowed radius, or the allowed orbit, the radii of the orbit, and we have also got an expression for the energy, right? Energy of each energy level, or the nth energy level has actually got this energy, and this is quantized, and it is given in terms of the electron charge, electron mass, then the E naught, permittivity of free space, H, the Planck's constant, etc., etc. Okay, so that is a very clear idea now that what is going on. Okay, now let us quickly take a small, detour and talk about De-Broglie hypothesis. So what did De-Broglie actually do? So as we saw, that light can be both a particle or a matter. Can be particle or wave, so not matter. Okay, so matter can be particle or wave too. That means the electron can also behave like a wave. Okay, so the linear momentum of a parallel light beam, say P, is given as epsilon by C, E by C. So E is, as we already know, is the energy that is carried. This is equal to H by lambda. Okay, so this is like the linear momentum of a single photon. Linear momentum of a single photon. Okay. For matter waves, this lambda, okay, should therefore be given as H by P. H is the Planck's constant, P is the momentum of the particle. So this is like an analogy. Momentum of the particle. So since H is about 6.6261 into 10 to the power of minus 34 joule second, okay, and the momentum is of a particle will be kind of small. Okay, So lambda is usually very small for large matter. So that means when you move, the wavelength associated with you is so small that it is almost undetectable. Okay? This is definitely not the case with fundamental particles. Okay, that means, for example, for an electron, lambda is nothing but h divided by mev, which is now given as 2 pi r into n. So it's an integer. So this lambda now becomes, right, an integer fraction of its orbital circumference. This is rather interesting. So this is for an electron, say. This is for an electron. So large matter wave, forget about that. Let's talk about electrons. Okay. So electron, if we do, then if you substitute all the quantities over here, you get this, something like this. And then, as you can see, that lambda of an electron is basically an integer fraction. Okay. Integer fraction of its orbital circumference. Wow. So this is quite good. So this is what we mean by, when you actually have this kind of a situation. So what happened was, and also people calculated the Rydberg constant from from the Bohr's model. It turned out to be, it was about 109,743 centimeter inverse. Compared it to the experimental calculation of the Rydberg constant is about 109,678 centimeter inverse. So these are kind of very close to each other. So that is what it is. So we could explain more or less the hydrogen spectrum with the Bohr's model by using the Bohr's postulate and stuff like that. Okay. So also the discrete energies can be always can be well represented pictorially also using the Bohr's model. But in general, despite its rather ad hoc linkage between classical and quantum concepts, the Bohr's model was very successful. It provided for the first time a robust explanation of the existence of stable electronic orbits in an atom. And its predictions actually matched with the experimental spectra of hydrogen, atomic hydrogen. Right? And it could also predict the Rydberg constant. So all these things were the good part of the Bohr's model, though it feels a little ad hoc because of the postulates, because of the way that it is stitched together. But he could explain the discrete energies, he could explain the transitions, he could explain a fundamental constant. He could also explain that why these electronic orbits are going to be very stable. So this was more or less a consistent theory which uses classical mechanics and tries to, explain some of the quantum mechanical concepts that we have over here. Okay, and we also saw the De-Broglie hypothesis that by what is matter wave and how matter wave is associated for large matter. The matter wavelength is very small. Not so when you are actually doing with an electronic orbit of an atomic hydrogen, for example. Okay, so we could actually get these two things. Now let us do a very quick problem. Say the De-Broglie wavelength. Rather like to show it by an example. Say a golf ball with a mass of about, mass of the ball is about 0.04 kg. It was traveling at a velocity of 35 meters per second. And then, of course, an electron in Bohr hydrogen atom. So this is just a quick calculation just to show. So first what we do, the linear momentum of the golf ball is basically mv, which is equal to 0.04 into 35, which is about 1.4 Newton second. So the De-Broglie wavelength lambda becomes h by d, which is 6.626 into 10 to the power minus 34 Joule second divided by 1.4 Newton second, which gives you 4.73 into 10 to the power minus 34 meter. So you can see how small this wavelength is. Very, very small indeed. And more massive objects will have even lower wavelength. So minus 34. So this is like, so it's much, much smaller than its size. Consequently, the matter waves do not have any influence on the dynamics. That's why you can hit a golf ball and you can predict where it is going to go. Well, the fluid mechanics part of it can be complicated, but technically it is still deterministic. So you can say where the ball will go, right? On the other hand, if we look at the electron now, so electrons P MeV is 9.109 10 to the power minus 31. This is the electron's mass into 2.19 into 10 to the power 6 meter per second. That is its velocity. So this gives you 1.99 into 10 to the power minus 24 Newton second. So the lambda for the electron will be h by d. So that is about 3.33 into 10 to the power minus 10 meter. So it is about 3.33 angstrom, which is comparable. So Bohr's first radius is about 1.06 angstrom. So these two are kind of comparable. So they are in the same ballpark. Therefore, we must expect quantum effects from atomic hydrogen, which we saw in its initial spectrum. Okay, so quantum effects, okay, like this duality is evident for electron, okay, as it circles the nucleus. So you cannot avoid it because these two are of the similar order, almost close. One is 1/3 of the other. So this is just to show that why the matter waves are like that, and we have provided a more or less good understanding that how the Bohr's model, though ad hoc, is actually successful in explaining many of the things in the hydrogen spectrum. But however, we can still see that there is a lot of lacunae. There is no clear-cut, theoretical perspective or theoretical framework as such. As such, we need to go to Schrodinger's wave equation, and that we will do in a heuristic fashion, not in a kind of a rigorous fashion. And we will see how the Schrodinger's wave equation can be used as a first stepping stone to explain the entire quantum mechanics. Okay, so see you in the next class. Thank you.